Good morning, good afternoon, and good evening. No matter which time zone you're in, welcome to my virtual talk today about deep compression at inline speed for all-flash array. We all love all-flash array for its consistent high throughput and low latency. This enables us to consolidate multiple workloads into a single unified storage platform. It is easy to manage and share big data among different applications. However, all-flash array still comes with a cost premium at the acquisition. So in this talk, I'm going to share with you how to lower the cost of all-flash array by up to 30% with deep compression at inline speed. I'll share with you our hardware platform, which is a programmable FPGA accelerator card. I'll talk about our simple software API, and then I'll dive a little bit into the wonderful world of hardware architectural design on FPGA device. I'll also talk about our compression algorithm development, and lastly, I show some of the benchmarks. Now, first, a few words about Pure Storage. Pure Storage started in 2009 as one of the pioneers for pure all-flash array for enterprise storage. Today, we have three major product lines. In the front of the center is the front flash array X, which is a performance-optimized 100% NVMe block storage system. And recently, we just announced Flash Array C, which is capacity optimized and built on 100% QLC flash. And last but not least is the FlashBlade system. It is a scale-out, unified fast file and object storage system. Last year, our annual revenue is $1.6 billion. Customers love our all-flash systems for its high performance and 7 lines of reliability. We are very proud of our certified NPS score of 82. Now, back to compression. Not all compressions are created equal. For data storage systems, the compression algorithms that we are interested in are lossless data compression algorithms. We can actually further divide these algorithms into two categories. The first one is inline compression. Inline compression is pretty fast. In general, x86 CPU can compress data at half a gigabyte per second or even faster. So some of the good inline compression algorithms are LZO, LZ4, and Z standards in fast mode. The other category is deep compression algorithms. Deep compression algorithms, typically, they can compress 30% more than inline compression. But it runs quite a bit of slower. In fact, in general, deep compression is about 10x slower than inline compression. Some of the examples are Z standard and Mermaid. And we have thousands of flash arrays deployed in our customers' site. And through our data analysis, we have discovered that not all data gets an equal chance at compression. In the flash systems we design at Pure Storage, we have compression in mind from day one. So that's why our systems always have 100% data gets inline compressed. However, deep compression is still opportunistic. typically it is done at garbage collection time when we have CPU cycles available. So it is understandable that for a system that is under sustained heavy load, and especially for arrays that is fairly big in size, then we have a significant amount of data that never actually get the chance to be deeply compressed. So how do we lower the cost of an all-flash array by up to 30%? The idea actually is really simple and straightforward. So today, we take the ingested data and perform inline compression with algorithms like LZO before we write to the NVRAM. And then after the data has been persisted to flash, and then we do opportunistic deep compression at a garbage collection time. So what if we change that picture a little bit so that we actually perform deep compression inline before we actually write the data into the NVRAM? If we are able to do that, then we pretty much guarantee that 100% of our data are deeply compressed. And because deep compression typically compress 30% better than inline compression, we can save we can have a dollar per gig savings up to 30%. So what is a good hardware platform to be able to deeply compress data at inline speed? We have found that a programmable FPGA accelerator card is a good choice. It is not only is able to achieve the target of being 10x faster than the CPU for deep compression, it is also power efficient. It also has very low NRE for hardware development. And what is also very important for us is that it's a programmable platform that enables us to continuously improve the algorithm, and also enables us to explore other offload opportunities besides compression. So why not ASIC? So there are actually a few off-the-shelf ASICs available to offload compression. But in general, they are all fixed gzip or zlab format. And to our standard, they are suboptimal in both compression speed and compression ratio. Some of the vendors have Z-stand on their roadmap. Z-stand is better. It decodes fast, but not necessarily the fastest. But these chips that promise Z-standard support are still years away to be commercially available. Now, the second choice is, what about custom in-house ASIC? That'd be a fun project. I have done quite a few leading edge networking chips in the past. And that was fun. So next time, when I ask my boss and get approval for about $100 million of budget and increase the team size by about 10x, I would definitely do that as the next fun project. Just kidding. So actually, even if you get the resources to do ASIC, one of the drawbacks of ASIC is that it always lags years behind in algorithm development. And if you are a company that sells flash in the billions of dollars, then every 1% of compression ratio improvement is tens of millions of dollars in savings each year. So let's look at our pure accelerator card. And this is an illustrator of our hardware compression offload card. It is a standard half height, half length PCIe adapter. Really, the only major component on this card is a mid-range FPGA device. It is currently capable of PCIe Gen 3 by 8, which amounts to about 6 gigabytes per second of throughput. In the software driver, we have a really lightweight VFL driver in the user space. One of the things that I have learned in the past doing hardware offload is that it's really helpful if we can keep the hardware API as simple and as stupid as possible. If an offload project requires a team of software engineers to work on compiler design, then we are in big trouble. On the other hand, if we just replace a commonly used software function with a hardware function call, then it is so much easier. So in our case, we have a software C function that takes a data block stored in a source buffer and compresses the data and output in a destination buffer. So we keep exactly the same function API, but just replace the CPU computations with a few PCI writes to notify the hardware about the source buffer address and the destination buffer address. And then let hardware just do the work. And the software just pull and wait for hardware to finish the work. And to make things even simpler, we make sure in hardware that all the compression requests are completed in strict FIFO order. Now we have chosen a hardware platform, and we have picked a really simple API. So the next thing that we need to decide is what kind of compression algorithm that we are going to implement in hardware. So if you look at like the many different flavor of compression algorithms available on the market today, they are generally all based on on two fundamental techniques. The first one is LZ lossless data compression, which was actually published in a paper in 1977. The other technique is entropy encoding. The most famous form of that is Huffman encoding, which was published in a paper in 1952. However, compression algorithms are still being actively developed. And different algorithms, they actually differentiate on the quality of LZ search and output encoding. Some of the good open source examples are gzip and zlib. And recently, LZ4 and zstand have been really popular. On the closed source side, we have LZO for inline compression and Mermaid for deep compression. So which algorithm do we actually pick to do in hardware? So we actually, before we decide on that, let's list our goals of our compression. So first, what we are looking for in our all-flash array is a block compression. The compression of block size is typically less than 64 kilobyte. And in most cases, it's actually less than 32 kilobyte, because we do not want to sacrifice the read latency. And the second thing that is super important for us is that the algorithm has to be able to support fast decoding in software. This is super critical because all our systems support non-disruptive upgrade. So any data that is written into our flash array can live forever. And we have to guarantee that any future hardware upgrade can still read the same data out at faster speed. And lastly, we, of course, want the best possible compression ratio for real workloads. So with all these three goals, we end up decided to take the hard path to do an in-house algorithm for compression. It is not easy, but at least we have the vast amount of data that is available for us across our tens of thousands of flash arrays to train our algorithm and to benchmark our algorithm against the best ones that are available on the open market. Now let's dive a little bit into the actual hardware design for compression on an FPGA device. So with a mid-range FPGA device, typically the logic can only run at a few hundred megahertz. So what makes it possible for such a device to be able to outperform CPU by 10x, even if the CPU can run at multiple gigahertz? Well, really the key is the freedom in architectural and logical design with a programmable hardware. If you look at a general purpose CPU, it has become more and more complex. But fundamentally, its architecture is still based on the same Von Neumann architecture that was described in 1945. It is a memory load and store architecture with a limited number of execution units. With FPGA device and the freedom in logical design, we can explore the inherent hardware parallelism. And also what is really helpful in these devices is it has thousands of SRAMs that has aggregated bandwidth in the neighborhood of terabytes per second. And I will show you the example of why that is super helpful. Let's take an example of how we actually take advantage of the abundance of memory blocks on a mid-range FPGA device. One of the essence of LZ search is to find duplicate strings in the data stream. And one way to do that is with a hash table. So at each byte position, you calculate the hash of the current byte string that you have seen and update the hash table. You also want to look at the hash table with a hash to see if you have possible match in the data that you have seen before. So in the hardware design, in our pipeline, we process 4 bytes positions on every clock cycle. So that means we have 4 hash table lookups, and we have 4 hash table updates. And at a frequency of about 300 megahertz, this amounts to about 19 gigabytes per second of memory bandwidth. And of course, we don't have to stop at just 1 hash table per compression engine. If we have 2 hash tables, that doubles to be 38 gigabytes per second. And we can easily put 4 compression engines into our FPGA device. And that aggregates to be 153 gigabytes per second of hash table memory bandwidth. So such a high memory bandwidth hash table can actually be fairly easily implemented on the FPGA device. So in this particular example, we just take 64 memory blocks, which with each memory block can independently perform one read and one write at every clock cycle independent of each other. So what is needed is really just a simple write after and read after. We distribute the 4 lookups and the 4 updates into the 64 distributed memory blocks. And because the hash lookup table and updates, the hashes are really just random numbers. So the memory conflict, memory access conflict actually is fairly low in the range of a few percentage. And that does not really degrade our LZ search quality. In our hardware compression engine, we also do Huffman encoding. And the LZ search gives us the literals and the metadata sections. The literals are the data bytes that we have not found any matches. And the metadata section describes the match that we have found. So for our Huffman encoding, we perform dynamic Huffman encoding for the literals. But we perform static table, static Huffman encoding with 64 static tables for the metadata sections. Our static tables are trained by the real workload across our fleet. And in order to increase the Huffman decoding speed, we do multi-string Huffman encoding for each data section and the literals. Now let's again dive a little bit into the hardware design for Huffman encoding. One of the critical paths for Huffman encoding is to sort the histograms. The way we implement Huffman encoding is each symbol is an 8-bit byte. So that means for each data block, we generate a histogram of 256 random numbers. And we need to sort 256 random numbers. A good sorting algorithm is a merge sort because it has predictable n log n cost. But if you just implement in hardware the naively, the n log n of 256 numbers still gives you 2,000 clock cycles. That is a very long latency. So how do you speed that up? So it's actually easy if you have the freedom to design your own hardware pipeline. So here is an example of how we actually implement our merge sort. So we have a hardware pipeline of 4 stages. On the first stage, we have 8 merge sort engines. Each can sort 32 numbers. So once we have generated the 256 histogram numbers, we just distribute it to all the 8 merge sort engines, and they start sorting the 32 numbers each they got independent of each other. Once all the 8 engines have completed their work, then we move to the second stage. The second stage is really simple. It's just a merge process. Imagine you have 2 sorted lists of numbers already. So it's really simple just to merge it into a single list of sorted numbers. And in this case, we should merge 2 list of 32 numbers into a list of solid 64 numbers. The same thing goes on stage 3 and stage 4, and after stage 4 we have a solid list of 256 numbers. Now, if we compute the latency of the hardware processing pipeline, it is 608 cycles, which is quite a bit of a speed up than the naive implementation of merge sort. But more importantly is because this is a pipeline design. So the processing pipeline can actually sustain one sort every 256 cycles. And this is really important for us to be able to sustain compression throughput, even for data block size that is less than 2 kilobytes. Now let's take a step back and look at some of the micro benchmarks. The first benchmark we run is against a block bench of data that is 32 kilobyte in size. We compare the performance of 6 different algorithms, and I'll describe each one later. The first column here is the encoding speed. The second column is the decoding speed. And the third column is the compression ratio. The speed is expressed in nanosecond per byte. Now, about the algorithms, on the chassis 0 and on the chassis 4, our in-house development software compression algorithms. And L0 Pro is a commercially available inline compression algorithm that we use in some of our systems. And Mermaid 4 is the deep compression commercial compression algorithm that we also use in some of our systems. Area 0 and Area 3 are our hardware compression engines. Area 0 is a hardware version that is perform inline compression. And Area 3 is really the interesting one. That is the hardware engine that is doing deep compression. So the first thing we can actually see from this benchmark is that with 32 kilobytes of data blocks, our hardware inline compression is actually faster than the best inline compression L0 Pro that is running with Intel CPU. Not only that, it's also actually compressed the data about 10 to 15% better. So that's really a win-win on both fronts. Now, if we look at our hardware deep compression engine, it is just slightly slower than the L0 inline compression running on software, but it actually performs more than 35% better in compression ratio. So that's a huge win. However, clearly, we have, in this case, there's still a room to improve. If we compare the compression ratio of our hardware deep compression engine against either Mermaid 4 or our chassis 4 deep compression algorithm, we still have about between 5 to 10% of room to improve. Now, next, let's look at the benchmarks with 4 kilobyte block size. In this case, we actually see that the encoding speed of hardware engine it's quite a bit of slower than what we would like to see compared to L0 inline compression. But actually there is this cost actually is not really in hardware. Our hardware actually is able to keep the same throughput regardless of the block size, from 32K all the way down to 2 kilobytes. We have discovered that we have quite a bit of software driver tuning that we need to perform for small blocks. Now, if you look at the compression ratio, and we still, it consistently beats the inline compression with up to 35% of better compression ratio. And interestingly, in this case, our hardware deep compression ratio RH3 is able to beat the best deep compression algorithm moment 4 that we can get our hands on the open market by about 10%. However, compared to our own in-house software deep compression ratio a la chassis 4, we still have another 10% room to improve in terms of compression ratio. So that brings us to our continuous algorithm development. So our roadmap for hardware compression is we are going to work on LZ plus. That means it's a better LZ search algorithm. LZ search is an NP hard problem, so there's always room to improve. Another feature that we are looking at is called filters. So basically, we want to be able to automatically detect certain data string types so that we can apply some possible transformations of the data to achieve better compression ratio. And of course, there's also the unknown, that is the new algorithm discoveries that's going to happen later. And with a programmable hardware platform, we have the possibility to adapt to that. So in summary, I've shared with you how deep compression at the inline speed can potentially lower the cost per gigabytes for all flash array up to 30%. And I hope you agree that FPGA accelerator card is a good choice of hardware platform to deliver on that promise. And I have shared with you that a domain-specific architecture and logic design is key to success. And we love our programmable platform because it enables us to do continuous improvement and non-disruptive field upgrade. And with that, that concludes my talk. Thank you very much. I hope you enjoyed it. If you have any comments, please leave it here. And if you have any questions about any of the materials, please feel free to contact me at my email address that is provided on the first page of the presentation material. Thank you very much. I hope you enjoy the rest of your virtual conference.